Okay, we're going to get started. You can see my homemade document camera, peanut butter, some oatmeal, and I'm gonna put some barbecue sauce on top of it so that my camera won't fall. And hopefully this table I'm working with won't fall either. It's my sewing table that's not ready for this experience, I don't think. Anyways, so based on y'all's feedback, I'm gonna start, probably this video will just have examples on complex numbers, and then I'll get a vectors one in. I'll work on that tomorrow. So I'm gonna kind of start at the beginning. I'm gonna try to break this up so that you can fast forward or whatever after I put this all together. So the first couple of questions were about like converting from one form to the other. So obviously we have seen before complex numbers. So I'm gonna just name two complex numbers, Z and W. And every complex number has a real part and an imaginary part. So a real part and an imaginary part. Sometimes maybe they have a 0 as a real or a 0 as the imaginary. So even right now when we see something that looks like a real number, if we're viewing it in a complex number system, it would actually have an imaginary portion. It would just be like a 0i. So this is like the standard form of a complex number, but we also call these rectangular form because we can plot them on a rectangular coordinate plane or a Cartesian coordinate plane or the XY coordinate plane. But all we do is we rename it. So like this is the real axis, this is the imaginary, instead of X and Y. So like 8 plus 2i means that it goes 8 units on the real. So come over to 8. And then 2 units up on the imaginary. And obviously I'm just sketching these, so they're not perfect. And then what we normally do is represent them as a vector. So when we talk about the length of an imaginary number, it's the modulus of this, which is just the length of it. So when we talk more about vectors, it has lots of different names, and we'll get to it in a second. So W, so let me name it. This is Z. W goes -3 on the real, so 3 on the left, and then it goes down 1 unit. So this would be W. So there we go. So this is Cartesian form again because we're placing it on a Cartesian or a rectangular form, a rectangular coordinate plane. We're just renaming it to suit our purposes. So this is a rectangular form. So being able to convert from rectangular into the polar, sometimes called the trigonometric. So some people use these interchangeably. So Study Island, I believe, is calling this form where we have R times the cosine of the angle plus I sine of the angle. So we're going to represent both of these in this form. So this is polar or trig form. It just depends on who's talking, but we all basically understand that both of these mean the same thing. There is a different form in the notes that I sent you. That's the true polar form. This is technically the trigonometric form, but for our purposes, it's fine because it's pretty easy to see the difference. Like it's not really a big difference at all. All right, so anyways, what does all of this stand for? So we're rewriting this. R is the modulus, which is the length. So I know you guys have walked through the notes or whatever. So it's always just the square root. So think of this as the hypotenuse of a right triangle. We can drop a perpendicular here. So this side would be 8. This would be 2, right? 2 and 8. So the hypotenuse would just be the square root of 8 squared plus 2 squared. So notice I'm not using the imaginary portion because that's just placing it on here. It's not actually showing us the length of that. So the modulus, the length, another way to write this since we're finding it for Z is using this notation. So 64 plus 4, this is the square root of 68. And for this lesson, I'm just going to leave that. I'm not going to simplify it, which is going to bother me, but I'm just going to leave it so we can always come back and reference it. We can do the same thing for W, the modulus of W, so we also call it R. It's a modulus It's the length of W. We can find it the same way, make a tiny little right triangle there. So it's A and B, right? So to find the hypotenuse here, so it's -3 squared plus -1 squared. So this is the square root of 10. So each of these have a modulus. We're just saying that those are the lengths. So our modulus of each of those are given by a formula. So the modulus of any complex number is always the square root of a squared plus b squared, or x squared plus y squared. It doesn't matter the variables, but it's always the real, and then b is the coefficient of the imaginary. So we're just using 2, or we're just using -1. We're not using the imaginary part. So this is important. So that's the first part of writing this in its trigonometric or polar form. Now we need to find theta. So theta is the argument, but essentially we use it to tell a direction. So what is the direction of the complex number? And we mean this in a very specific way. Theta should always be between -pi and +pi. So it should be represented in radians. So radians are super important here. I'm going to show you some in degrees just because our brains obviously work easier in degrees. And then we're going to focus on converting that over to radians, making our brains work in radians a little bit. So it's okay to have decimals here. So it's all fine. We're all fine. Everything's fine. So theta is always the angle made with the positive x axis. In this case, that would be the positive real axis. So that's why we're saying it's from -pi. So it's got to be here because we're talking about this guy over this way. So theta. So we want to know what's this angle right here. That's a theta. So what's that angle? So again, we go back to this right triangle that we talked about. So if we know this is 8 and we know this is 2, what can we do to find theta? So the angle, the argument of a complex number is always going to be the inverse tangent. And it's always, we want to use the tangent ratio, opposite over adjacent. Opposite over adjacent. So in this case, it's 2/8. So this would be the argument of z. The argument of z is theta. We can find the argument of w. It's also theta. And it's the inverse tangent of, so I'm again going back to this right triangle. So this time we're using negatives because we're in quadrant 3. It's -1 over -3. So opposite over adjacent, because here's our theta. So when we do this, I am gonna just plug these into my calculator. And again, I'm going to put this on degree mode because it's easier for right now. So the angle that z, the argument of z, the angle that we see right here is approximately, and I'm rounding here to 14 degrees. It's 14.0 blah, 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 but it's 14 degrees. The argument of w, though, when we put this into our calculator, remember we're using an inverse tangent. Inverse tangent is going to give us, its outputs are from -90 degrees, -pi/2 to +pi/2. So that would be, you guys can't see that, that would be these quadrants. And we can see that this is not in those two quadrants. So what I mean by that is when we put this into the calculator, it's actually going to, the negatives cancel, so it gives us an angle in quadrant 1 of 18.4 degrees. And clearly we can see that it's not 18.4 degrees to get all the way over here. What it's talking about is this little guy right here, right? This angle is 18.4 degrees. I don't want that little angle. I want the argument, and we know that the argument's always going to be an angle made with the positive real axis. So what I'm going to do is go back. This is a reference angle. It's 18.4 degrees away from this axis. So what I want to do, because it's in quadrant 3, is come around this way. I don't want to go all the way around because I have boundaries. I'm not allowed to go outside of those. So what I'm going to do is 180 degrees minus 18.4 degrees. And again, I'm rounding here, but this gives me about 161.6 degrees. But I don't want to go this direction. I want to go this direction. So the argument of W is actually approximately -161.6 degrees. So now I can go back and say, if I want the polar or the trigonometric form of z and of w, I have everything I need here. So we sometimes abbreviate this because we're lazy. So I'm going to show you the abbreviation. So z would be the modulus of z, which is the square root of 68. You should simplify that. Square root of 68. Instead of writing cosine theta, and our theta is the, 14 degrees, plus I sine of 14 degrees, the abbreviation is CIS 14 degrees. So where do you think that CIS comes from? Cosine plus I sine. The theta gets used twice. So that's where it's coming from. W is the square root of 10, its modulus. Cosine of theta plus the I sine of theta, and this theta is negative 161.6 degrees. And again, that's not perfect. Those should be in radians, but for the purposes of this explanation, I wanted to show you guys what these are in degrees. So there you go. If we wanted to then convert back from z and its polar form back to its rectangular form, all you do is simplify it. And by that I mean, if you look up here, the cosine of 14 degrees. Now, we don't know what that is. It's not a unit circle value, but you can use your calculator. So it would be the cosine of 14 degrees plus I, and then again in my calculator, I would say the sine of 14 degrees. And then I would multiply it by the square root of 68, because that's what r is. So I would just distribute those. And because we rounded, we're not going to get exactly what this is, but we would get really close. So usually when you're asked to convert something from its trig or polar form back to its Cartesian or rectangular form, it's an angle on the unit circle. So you would know exactly what these outputs are. But to go backwards, all you're doing is just plugging in the angles and then multiplying. And that's it. Okay, so if you watch the notes, fantastic. If not, that's cool. Here's an example for you. Just really quick, just converting another one. So we're going to convert, let's say, square root of 3 plus I to polar form. So we want, I'm just going to call this, I don't know, W, whatever. So W equals square root of 3 plus I. I want to represent W in its polar form, so R cis theta. So first thing we do is find R, modulus. So that's the modulus of W. Square root of 3 squared is 3, plus, I just take this coefficient, 1 squared, 1. Square root of 3 plus 1. Square root of 4, that is 2. All right, and then theta, inverse tangent. So it's always 1 over the square root of 3. It's always b over a, or y over x, however you took your notes on that. So 1 over the square root of 3, I don't need a calculator for this. This is a unit circle value, so what angles on the unit circle have this specific tangent ratio? So that's really root 3 over 3, and those are 30-degree reference angles. But we don't want 30 degrees, we want this in radians, so we're going to rewrite it as pi over 6 because we are very smart people. So W in its polar form, so we took it from square root of 3 plus I, and its polar form is 2 times the cosine of pi over 6 plus I times the sine of pi over 6, also known as 2 CIS or cis pi over 6. That's it. So there's one example. We can do a different one. I can show you how to go from polar to rectangular. So again, let's say I had convert 4. I'll be lazy. I'm going to do this in degrees first. So let's convert this to rectangular form. So what does this mean? Again, it's easier. You know, I'm lazy, but for you guys, it would be easier to do this conversion if you wrote it out. So 4 times the cosine of 240 degrees plus I times the sine of 240 degrees. So all I'm doing is simplifying. What is the cosine of 240 degrees? Well, 240 degrees is a 60-degree reference angle, but it's in quadrant 3. So what is a 60-degree angle? What do the coordinates look like? We can do our hand trick, right? So 0, 30, 45, 60. So this would be 1/2 square root of 3 over 2. And because we're in quadrant 3, they're both negative. Okay, so the cosine of 240 degrees is negative 1/2. So I'm done with it. Plus I times the sine of 240 degrees is negative square root of 3 over 2. So now all I have to do is distribute the 4. I can't combine these, they're not alike. So 4 times negative 1/2 is negative 2. 4 times I times negative square root of 3 over 2. So the 4 and the 2 can get simplified. What I end up with is negative 2 root 3. Oops, I forgot my I, duh. So the I has to go there, and that is the rectangular, the complex, or the Cartesian form of this polar number. And it's just as easy as that. We are done with that. All right, the next thing we're going to talk about is De Moivre's theorem, and the reason that we're using De Moivre's theorem is to actually make your life easier, and I want to show you why. So if we go back to some of those complex numbers that I defined for you at the beginning, so let's go back to, I think I called it Z, and I think I said Z was 8 plus 2i, who knows, if not, there's Z. Okay, and let's say that Ms. Schaefer asked you to find Z to the 8th power. So we're taking this number and we're raising it to the 8th power. So essentially we would treat this like a binomial, which means it would be 8 plus 2i to the 8th power, which would mean 8 plus 2i times 8 plus 2i times 8 plus 2i times blah, blah, blah. And we would keep going until we had multiplied this by itself 8 times. And then how do we do that? Well, it's a bunch of FOILing or double distributing or triple distributing or whatever. It would take a really long time. So luckily, this man, we know he's a man, right? White man, I'm sure, came along, felt super important because he found this pattern. So yes, it's really cool and we appreciate him for doing that. And you know what happens when these old white guys find out something neat, they name it after themselves. So here is De Moivre's theorem. He actually noticed that if we're raising a complex number to a power, it's easier to do that in its polar or trigonometric form. So I'm not going to prove that to you right now because it's pretty complicated. That would be like a really long video. But I am going to send you the link to it because it's interesting. So I know some of you really like doing stuff like that, and you know, some of us don't, and that's okay. But I'll send you the link, I'll put it in this video, and you can go and check that out. So let me just show you what De Moivre figured out though. Initially, what we have to do first is put it in polar form. So to put a number in polar form, we need r and we need theta. We need the modulus, we need the argument. So we already found that information out about these, right? So we knew that the, we did this one, right? Yeah, anyways, r, the modulus of z, is the square root of 64 plus 4, so the square root of 68. Oh yeah, that's right, because I wasn't going to simplify it. That's fine, we still won't. Ew. Okay, and then we needed to find theta. So for this one, I think it was the 14 degrees. I'm going to go backwards. Yes. So the argument was 14 degrees. So z's polar form, root 68. There we go. All right, so now when we take this to the 8th, we're taking this whole thing to the 8th power. And so the formula that he discovered, or the pattern, and then now we've made it into a formula, just says that anytime you have a plus bi to the nth power, it's going to be r to the nth power, so the modulus to whatever this exponent is, times the cosine of n times the argument, plus I times the sine of n times the argument. And again, n is just whatever you're raising it to. So for this guy right here, we would say that z to the 8th is the r value, so the square root of 68, we're raising it to the 8th power, times the cosine of n, which is 8, times the angle, 8 times 14. I don't have a calculator in front of me right now. I had to go change its batteries, so it's not here. But I'm confident that you guys could multiply that out and figure it out. And here, the square root of 68, you can, you can always simplify these. Well, not always, but usually. So just remember what the square root of 68 means. 68 to the 1/2 power. We're raising that to the 8th. When we raise an exponent to an exponent, we multiply them. So 1/2 of 8 becomes, this is really just 68 to the 4th power instead of the square root of 68 to the 8th. But whatever. And then again, we would finish this and just write it right here. It'd be nice, but it would be, you could do cis of whatever 18 times 4 is, which clearly I could do in my head if I tried, but I don't feel like it. And you guys probably all have calculators, so you could just do it because you love me. All right, so that is de Moivre's theorem. It works every single time. It's the same set of steps. You just keep going and going and going and going and plugging and chugging. So if you're interested in that proof, go ahead and check it out. Okay, this will be the last video for this section. So this is the most complicated part, so roots of complex numbers, and I'm going to do my best to make this easier for you. And I'm going to start that by choosing a number that you guys already know a root of. So I'm going to say, let's start with an easy question. If I wanted to know the cube root of 8. So what is the cube root of 8? If we're working in the real number system, very easy. There's one answer. What number do you multiply by itself 3 times to equal 8? 2. That's it. So easy. But let's say that this 8 didn't exist just in the real number system. Instead, it existed in the complex number system. How would we write 8 as a complex number? Well, there's no imaginary part to it, so this would be 8 plus 0i, right? 8 plus 0i. And if we wanted to know the cube root of the complex number 8, which is 8 plus 0i, there's a theorem that says whatever the root is that you're looking for, the nth root, whatever the nth root is, a complex number will have that many roots. So if I wanted the cube root of 8 plus 0i, there are actually 3 answers. So 3 answers because I want the cube root of this complex number. So if I wanted the 12th root, I would have 12 answers. If I wanted the 100th root, I would have 100 answers. And it's not very difficult to find them once you understand this process. So I'm going to show you how to find the initial ones and then where the other ones kind of fall out after that. So every time you're asked for a root, whatever this number is, that's how many answers it has. Okay, so let's see, how do I want to start this? So first thing, make sure it's in its polar form. So let's get this complex number to its polar form. So in order to do that, we need our modulus. So in this case, it's just, don't let the 0 trick you, it's fine, right? So 8 squared and 0 squared, that would just be the square root of 64, which is 8. So the modulus of this is 8. And if you think about what the graph of this looks like for a second. So if it's 8 plus 0i, if this is the real and this is the imaginary axis, all we've done is go over here 8. And we're just this little guy right here. We're nowhere, we haven't moved up or down on the imaginary axis. So what's the length of this line? Makes sense that it would be 8. Now when we look at this, it may make a little more sense to find the argument. So the argument, the inverse tangent. So if I think about this, it would be 0 over 8. If I use the equation, so we can't really make a right triangle here. So I don't even really need to do that. I can just use my brain. What's this angle? Well, it's 0 radians, right? We're radian land, so we're 0 radians. So z as its polar form is 8 cis 0. Easy, super easy, right? So here's what I want you guys to think about. If we know that this number has 3 answers, let's call one of the answers W. So W is one of the answers here. And if W is a cube root, then if we cubed W, it would have to equal 8. So think about it. If we know that the cube root of the real number 8 is equal to 2, what I'm saying is W is 2, and W cubed is equal to 8. So right now we don't quite know the answer, so I can't say 2 cubed equals 8 because this isn't a real number. So I'm just calling it W. So if W to the 3rd power equals 8, and I wanted to solve for W, right? I want the answer. Well, how would I solve for W? I would get the cube root, right? The cube root of both sides would help me solve for W. So I can turn this into W equals the cube root of 8, but what I want to write that as is 8 to the 1/3 power, right? 8 to the 1/3 power. But we don't have just this plain old 8, right? And I should have done this a second ago. We're not really finding, I meant to write this instead of this real number 8 of this. So that's what we're doing. 8 cis 0. That's what needs to be raised to the 1/3 power. 8 was the real number. We want this guy right here. So again, I just did two things. I rewrote my real number as it's, we did it as a complex, and then the complex as a polar, and then what might have confused you is I took the cube root of both sides. Really all I'm doing is raising this to the 1/3 and they cancel. That's what I did. I raised this side to the 1/3. All right, so now that we're there, what we're using, if we have this number raised to the 1/3 power, that's de Moivre's theorem. So we just saw an example of de Moivre's theorem raising it to a whole number exponent. This time we're just raising it to a fractional exponent, which doesn't really matter. It doesn't really matter what we raise it to. De Moivre is still going to help us out. So if we want the answer, which we call W here, the root, one of the cube roots, W is, if I'm raising a polar number to a power, I use de Moivre's. So it's 8 to the 1/3 power, cube root of 8, times the cosine of 1/3 times the angle. Oops, but the angle is just 0. I didn't mean to write theta. Plus I times the sine, according to de Moivre, in times the angle. So W is 8 to the 1/3 is 2 times the cosine of 1/3 of 0. It's still the cosine of 0 plus I, the sine of 0. 2 times the cosine of 0 is 1 plus the sine of 0 is 0, 0i. So 2 times 1 plus 0i is just 2. So this is the answer we got, because we know that the cube root of 8 is equal to 2. So what we need to think about is how to generate the other 2 missing answers. We have one of them, it's 2. We can solve it this way. Here's our first answer. How do we find the other ones? So if you think about what's going to happen is we're just going to take iterations of this angle. So if this is 0 degrees, I still want to represent this as the same way. So I'm taking this angle 0 degrees and I'm rotating it, and I'm rotating it, and I'm rotating. And remember, we can rotate this angle as many times as we want to, and still end up in the same exact spot. So we're adding iterations of 2 pi. So I'm taking 2 pi and I'm rotating it a lot and a lot and a lot. Now, when we did this in class, when we solved for trig equations, we did 2 pi n. I'm not going to use n here because we're already using an n value. That's what 1/3 is, right? That's when we raise it to an exponent. So we just pick a different letter. It's k. So when I'm finding my cube roots, or any of my roots, it's always going to be this gets added to theta, or the argument, each time. So I'm adding it to theta. I'm not adding it to the answers, because this is, we're talking about rotating this around and around and around. So when I'm solving this, what I'm really doing is finding 8 to the 1/3 times the cosine of 1/3 times 0, why do I keep doing that? 0 plus 2 pi k plus I times the sine of 1/3 0 plus 2 pi k. So I'm taking the 2 pi k and I'm rotating this angle over and over and over and over. So the first one I find is when I have no rotations, right? No rotations, that's why I'm using a 0 here. I'm not rotating it, I want to find the initial one. So if I put a 0 in for k, 2 pi times 0 goes away, and I'm still just finding exactly what we found up here. So the initial root is 2. It's when k is equal to 0. Now let's find the next root, and we know we have 2 more. So I always start at 0, and then I'm counting up until I have as many roots as I'm supposed to have according to the problem. So 8 to the 1/3 power again is 2 times the cosine. So it's 1/3 times 0 plus 2 pi times k, where k is going to be this number each time, my next root. So if k is equal to 1, it's 1/3 of 0 plus 2 pi plus I times the sine of 1/3 0 plus 2 pi times k, which is 1. 0 plus 2 pi. I'm going to do the same thing here. So it's 8 to the 1/3, 2 cosine 1/3 times 0 plus 2 pi times k. K is 2. So it's 0 plus 4 pi. Do you see how we're taking 0? It was 0 radians. Now we're at 2 pi radians, and then we're at 4 pi radians. So not every one of these is going to have 0 as its initial starting point, like meaning all of these 0. They're not all going to have the same argument, but the process is always the same. You're always adding iterations of 2 pi, another coterminal, coterminal, coterminal. That's what we're doing each time. So let me finish this one off before I forget what I'm doing. It's just like class, right? All right, so if I simplify all of these, I should have left more space, my bad. I'll just come down here. So W1, if I simplify W1, so again, W0 is just that first one where we're not adding or subtracting anything to the angle. W1, now I'm adding an iteration. W2, I'm adding a second iteration. That's why we're adding 4 pi. All right, so I'm going to do W1 down here. So it is 2 times. So the cosine of 1/3 of 0 plus 2 pi. So 0 plus 2 pi, 2 pi times 1/3. So I have the cosine of 2 pi over 3 plus I times the sine, same deal here, 2 pi over 3. And W2 is 2 times the cosine, same idea here, 4 pi over 3, that's a 3, plus I sine of 4 pi over 3. And now I just gotta know my unit circle. So 2 pi over 3 and 4 pi over 3, those are 60-degree reference angles. Write that down, 60-degree reference angles. You can use your hand trick, right? 60 degrees, boop. 1/2 square root of 3 over 2. And 2 pi over 3, the cosine will be negative here. So it's 2 times negative 1/2 plus I. The sine of 2 pi over 3 is positive. Square root of 3 over 2. And I'm just going to distribute. So 2 times negative 1/2 is negative 1. And then, multiply. I got a text. I got distracted. Just like you. It's just like class, everyone. Okay, so negative 1, I'm distributing here. So this is I on the square root of 3. So that's our second root. And then finally down here, 2 times the cosine of 4 pi over 3. We're in quadrant 3 now. And this is going to be a negative 1/2 again. And the only difference is now 4 pi over 3. It's going to have a negative square root of 3 over 2. So I'm going to say negative I square root of 3 over 2 to save myself some room. Distribute. Negative 1 minus I on the square root of 3. So here's one root. Here's the other root. And here's the other root. So there are 3 roots to this. Now, something interesting about this, and I'm not going to show this to you right now because I know that you are all capable of doing this, is if you found the modulus or the length of each of these numbers, so remember we can write this one as 2 plus 0i, they are all the exact same distance from the origin. So they're exactly the same distance from the origin, and that has to be true. So that's how you can always check your answers. So the fact that these two look almost identical isn't always going to happen. It happens a lot, but it's not always going to happen. So if you found the modulus of each of these two and this one, all of them would end up being exactly the same. Another interesting fact, if you were to plug this number into your calculator, now you'd have to change the mode. So push your mode button, go down, there's actually an imaginary version or a complex version of complex mode, and you type this in and raise that number to the third power, and guess what you would get? You would get 8. You would get 8, and it would be amazing. So I do plan on showing you guys that once I find some batteries for my calculator. My bad. Okay, I'm gonna do one more of those finding roots for you guys, and then this is the most talking I've done in over a week, so I'm gonna go rest my voice. This is ridiculous. I can't wait to go back to school. So I'm gonna start with one, I don't know, I'm gonna do square roots. So let's find the square roots of, so I'm gonna use a complex number. So this time I'm gonna use like, let's do this. Yeah, I think that one will work. Okay, so this one's a little bit different. We don't have a starting point this time, and that's okay. So that's actually more normal. So here's the process, and it's always going to be the same. The first thing you should do is figure out what is your n value. So how many roots am I looking for here? So square root's pretty easy. So square roots, n is 2, meaning I need 2 answers. So if I asked for the 4th roots, you would have 4 answers. If I asked for the 12th roots, you would have 12 answers. All right, then we want to put this into its polar form, meaning we need to find an r value. What is the modulus of this number? The square root of 2 squared plus, so I'm leaving the I out. Don't shoot your eye out. This is 4 plus this, don't let this beat you, 2 square roots of 3 squared. We square, we square. So 4 square root of 3 squared is still 3. So this is 12. So we end up getting, oh, that was nice, the square root of 16, which is 4, in case you forgot. So there's our modulus. Now we need our argument. Inverse tangent of 2 root 3 over 2. 2's cancel. I'm looking for where is the tangent equal to the square root of 3. That is a 60-degree reference angle, otherwise known as pi over 3. Which now makes me question, did we do something wrong before? No, those were 60 degree. Okay. Anyways, so pi over 3, where am I? Okay, so we can rewrite this. So I'm just gonna define it as z, doesn't matter, you can pick whatever letter you want. So z is 4 cis pi over 3. Ew, that's ugly. Pi over 3. All right, so when we go to find the roots though, I want to find iterations of pi over 3. So I'm actually gonna take pi over 3 plus 2 pi k. It's always this process. Always, 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 always. Always plus 2 pi k. We start where k equals 0 and we count up until we have as many answers as we need. So in this case, k is just gonna have to equal 0 and 1. That's it. Okay, so it's always just plus 2 pi k. That's it. And then k is however many numbers it needs to be to get you a list of answers, and you always start at 0. All right, so the first thing I'm gonna do is just write w sub k, where w is my answer. So I'm subbing k, just so I'm gonna write in a formula, and then I'm gonna plug in 0, and then I'm gonna plug in 1, and I'm gonna be done, done, done. So this would be 4 cis pi over 3 plus 2 pi k because I want the square roots, I'm raising it to the 1/2 power. So it's important you remember these rational exponents for your roots now. So reach back to your geometry class. It's been a long time and I taught this to some of you, so I know that you know it. So I'm writing it this way so I can use de Moivre's theorem, right? So W sub k would be 4 to the 1/2 power. And now I'm going to go ahead and expand this times the cosine of, so I'm taking 1/2 and I'm multiplying it by this angle. So 1/2 times pi over 3 is pi over 6, plus I have to also multiply it by this, or I have the option of combining these, it's up to you, but 2 pi over k times 1/2 means I'm dividing that, so it's pi k, plus I sine, the same deal, so it's going to actually be exactly the same. It's always going to be exactly the same. There we go. All right, so now I've applied de Moivre's, and now I just need to simplify. So the initial root when k is equal to 0, I always start at 0. 4 to the 1/2 power means the square root of 4, it's 2, times the cosine of pi over 6 plus pi times k, where k is 0. So this is just the cosine of pi over 6. Remember, I should always just go back. Sorry, this one didn't start at 0. It started at pi over 3. So forget what I was even about to say. I just multiplied it by 1/2. That's fine. Ignore me. All right, plus I sine, again, k is equal to 0, pi over 6. And I could simplify this. So it's 2 times the cosine of pi over 6. Pi over 6 is a 30-degree angle in quadrant 1, so it's square root of 3 over 2, plus I, and then the sine is 1/2. Right, so the first root, I'm just going to distribute, is the square root of 3. I'm going to distribute, plus I. And then I'm going to do my next root, 2 times the cosine, so I'm going back up here, pi times k, right? So it's pi over 6 plus pi times k, where k is 1 now. So it's just plus pi, plus I sine of pi over 6 plus pi. And now I'm going to simplify 2 times. So pi over 6 plus pi, you can rewrite this, obviously. We're adding fractions here. So pi over 6 plus 6 pi over 6 is the cosine of 7 pi over cx, plus I times the sine of 7 pi over cx. Okay, 2 times 7 pi over 6, 30-degree reference angle, right? 30-degree reference angle, but this time it's in quadrant 3, so both of these are going to be negative. So I'm going to have negative square root of 3 over 2 plus I times negative 1/2, which is, I'm just distributing negative square root of 3 and then minus I. Root and root. I needed 2 roots. Here we go. I have them both. Yay! Anyways, I hope this helped, and I will do some more later.